has just died a brilliant death in an explosion equivalent to about 3.0 times 10 to the 28 megatons of TNT, a Type 1a supernova. Before we begin on Type 1a supernovae, let's first explain the primary explosive factor, a white dwarf. White dwarf stars are the remnants of low to medium mass stars after they run out of fuel. For example, let's fast forward about 5 to 6 billion years. Our star, the Sun, will be reaching the end of its life. Low on hydrogen fuel, it will swell into a red giant. After a few thousand years, it will completely run out of fuel and nuclear fusion will stop. The unstable star expels its outer layers and the core collapses onto itself, leaving a hot, around 100,000 Kelvin, extremely dense white dwarf, an Earth-sized star that is roughly 60 to 140% the mass of the Sun as it is now. Many Sun-like stars that become white dwarfs will cool off over the next billion or so years. However, some stars are in binary systems, that is, two stars orbiting each other. These circumstances allow a Type 1a supernova to happen. Here are the series of events that lead up to a Type 1a supernova with a binary star system of a white dwarf and large companion star. Two low to medium mass stars orbit each other. The more massive star's life begins to end first and it swells into a red giant. Some of the gas from the red giant spills into its smaller companion star. This creates a sort of envelope. The core of the red giant is left over. Both stars begin to spiral inward and the envelope is expelled. The red giant's core collapses into a white dwarf. Now, the companion star reaches the end of its life and swells into a red giant. Matter from the red giant spills into the white dwarf. Mass accumulates in the white dwarf until it hits the Chandrasekhar limit. As hot as white dwarfs are, they are not hot enough to begin carbon fusion. Electron degeneracy pressure, outward pressure created because no two electrons can occupy the same state, a direct consequence from the Pauli exclusion principle, works in place of fusion to keep the white dwarf from collapsing further. The Chandrasekhar limit is when enough mass is accumulated that the white dwarf has now become as massive as about 1.4 suns. The electron degeneracy pressure is no longer significant enough to prevent collapse. The carbon within ignites, that is, it starts fusion, and the white dwarf, with no outer layers to absorb the excess energy, explodes, a Type 1a supernova. The massive explosion causes the red giant companion to be shot off into space. This isn't the only method, however. A Type 1a supernova can also occur if two white dwarfs merge. Two white dwarfs orbit each other. The smaller dwarf is attracted to the larger and spirals inward. As they get closer, the white dwarfs transfer mass between each other. One of two things can happen. First, the larger dwarf can rip the smaller one apart, reach critical mass, and explode. Second, they can crash and merge completely, causing an explosion. Either way, enough mass and heat is accumulated to start carbon fusion, which causes the explosion. This massive explosion is a catastrophe for the star, but supernovae to us here on Earth are like lighthouses to sailors. Astronomers use Type 1a supernovae for their extreme brightness as a standard candle. In fact, a Type 1a supernova is so bright that it can outshine all of the other stars in its galaxy, or even tell us where an unseen galaxy is. Using an inverse square law, astronomers can determine how far away a supernova occurred. For many years, astronomers thought that the white dwarf large companion method was the most common way for a Type 1a supernova to happen. However, there is evidence to suggest that the number of white dwarfs close enough to the Chandrasekhar limit is not enough to get the number of Type 1a supernovae happening. Now astronomers are looking more into the merger method, and there has been a recent and very exciting discovery. NASA's Kepler and Swift spacecraft have been able to collect data before, during, and after three separate Type 1a supernovae, two of them being white dwarf mergers. This has provided valuable early-time light curves for the supernovae. Another recent Type 1a supernova was also seen by a mysterious force that is believed to be causing the acceleration of the expansion of the universe. More new and old galaxies, along with their stars, are moving much farther apart. By studying the age of supernovae at explosion of these faraway galaxies, specifically Type 1a supernovae, astronomers may be able to discern how they evolve with time and, in turn, better understand dark energy itself. If you're interested in learning more about Type 1a supernovae, NASA.gov is an excellent reference. The other sources listed here have excellent information as well.